Okay, let's go ahead and work this one out. So, if you're given 5 moles of glucose, how many moles of carbon, oxygen, and hydrogen do you have? So let's start with the first one. How many moles of carbon do you have?
30.
You okay with there being 30?
Yes.
Everybody okay with 30? How about this?
Wait, how do
If you had 1 mole, just 1 mole of glucose, okay, how many moles of carbon atoms would you have?
6.
You okay with that? Every single time you have a glucose, you've got 6 carbon atoms. So whatever the number is for glucose, it's that number times 6 for the carbons. So in this case, we've got 5 moles of glucose. So we must have 30 moles of carbon for every one. I mean, we could do a railroad track for this. Sure. There you go. So what is it going to be for oxygen? Also 30, right? And what's it going to be for hydrogen? 60? Okay. What's the total mass of 5 moles of glucose? All right, so 5 moles, C6H12O6. And then for every 1 mole, C6H12O6. That's in some grams of C6H12O6. Somebody have a number for that? For this mass here? Say again? 12.011 times 6 plus 15.9994 times 6 plus 1.00795 times 12. Yep. 180.158 times 5. So 900 grams. That would be a lot of glucose. Okay, so what are we going to do on the other side of this equation? What's the state of these things that are already written? Why do they have to be aqueous? Okay, so they're soluble because of the bromine and they're soluble because of the nitrate, but how do you know there's water there? Because they're 2 salts, right? And if I just threw 2 salts into a beaker together, nothing would happen. I need to get the ions to let go of each other, and in this case I would do that by just tossing some water in. So I've got a test tube or a beaker of the aqueous magnesium bromide and a test tube, a beaker of aqueous silver nitrate, and then I mix the 2 together. That's what the arrow is. So what do I have on the other side?
Silver and bromide.
So what's the formula?
AgBr.
Yep, AgBr.
G. And
Okay, so then I'm going to need a 2 there and a 2 there. And then what's the state for this one? Solid, because the silver but the magnesium nitrate is going to be aqueous because of the nitrate. Okay. What are the names of these things? Next one. Next one. The last one. Okay. So can you imagine when you get this question, you might just get magnesium bromide and silver nitrate react? Because I'm expecting you to already know how to get the formula from those, right? So the full ionic equation, what does it look like for the first part?
Mg.
That it? Just an Mg?
Solid.
Absolutely not. 110% no freaking way.
Oh yeah.
Mg, is it Mg though?
My bad.
Is it Mg? A little bit more.
Oh,
Mg plus
plus BR minus.
Oh.
It's a +2, right? It's magnesium. Mg +2, aqueous. Plus Br negative, aqueous.
Yeah.
2.
Plus.
We okay with where I put that 2?
Yeah.
What does this right here mean?
1. They're
Not this, this. They are already separated. That MgBr2 aqueous already means what has happened. They've already been dissolved, they're separated out. So technically what I really have inside the test tube that's holding that aqueous magnesium bromide is magnesium plus 2s. For every one of those I have 2 Br with a minus sign aqueous, yeah.
Then why did you add I'm just confused why you added the 2 on,
The AgBr?
yeah.
Because there are 2 bromines, right?
Yeah. But
On the left.
Is that saying there's 2, so,
Which 2?
the 2 in front of the silver bromide?
This 2 right here?
Yeah.
What is this 2 saying?
There's 2 of that.
2 of that whole thing.
Oh.
2 AgBrs. So how many Brs are on the right side? Because right? So 2 BRs. So one more time, everybody's okay with this 2 right here?
Yes.
Is anybody confused by where this 2 came from? It's okay if you are, just say so. Okay, so you see that there's a 2 up here, right? So this molecule right here is 1 magnesium with a +2 charge and 2 bromines, each with a -1 charge. And then what does this AQ part down here mean? It's aqueous, but what does that mean? More. That they're dissolved in water. When this aqueous substance dissolves in water, what does it do, Isaac? They split apart. This molecule, which is 3 ions, 1 magnesium and 2 bromines, breaks apart into 3 pieces. So what am I showing down here? Takes into 3 pieces. So here's 1 piece, the magnesium, and then here's 2 pieces of bromine that are floating around free. We good with that?
Yeah.
So technically it's just like shortening it just like you would with the net. Like you could write 2 bromines, right? Like plus Br.
This thing right here is just the shorthand way to write this full ionic equation.
Yeah, but with the 2 in front of the.
You're right, I could erase the 2 and write Br negative aqueous. I could write it twice, but I'm not gonna do that. Nobody will do that. Well, I mean, somebody might do that, but I'm definitely not gonna do that. Okay, so now what do I write? What comes next? Plus, excellent, good start. Plus 2 Ag positive aqueous. We okay with that? I'm not okay with this thing. What is that doing? So where did the 2 silver pluses come from? There are 2 silver nitrates up there for every 1 magnesium bromide, so I need 2 silver ions down there. So then I write a plus, and what comes next? 2 NO3 negative aqueous. We okay with that? Yeah, because now the coefficient is out front of the nitrate, so it's 2 of what follows. Not the when you have a parentheses and a subscript, that means those 2 things inside the parentheses are connected to something, and right now they're not connected to anything. All right, and on the other side, what do I write here? Why am I not busting them apart? Because they aren't broken apart. The only reason I broke the things apart on the other side is because they actually technically are already separated. So with it, silver bromide as a solid, they stay stuck together because they are stuck together. When this reaction happens, you see white stuff floating around inside the container, falling to the bottom of the container, stuck together AgBr. And what do I do for the end here? That? Thanks. Who are the spectator ions?
Magnesium and nitrate.
The magnesium and the nitrate are the spectator ions? Why is that? There's no change for them on either side of the arrow, right? On the left side, it's Mg plus 2 aqueous. Right side, Mg plus 2 aqueous. On the left side, 2 NO3 negative aqueous. Right side, 2 NO3 aqueous. So nothing changes. But the bromines and the silvers came together. They used to be aqueous, and now they're solids. So what's my net ionic equation?
2Br minus
Yikes, that's terrible. You could put them, but what's going to happen if I put all the 2's there? There's going to be a 2 in front of everything. So then what could you do? You could just divide through by 2. So if you want to put the 2's there, go ahead. If you don't want to, you don't have to. So maybe putting the 2's in there is a good idea. We all happy with those? All right, so we're going to write a balanced chemical equation for the combustion of propane gas in oxygen, and we're going to start with 25 grams of propane. How many grams of water am I going to make? Okay, so this is propane, so C3H8 gas plus O2 gas turning into, looks like a 4. Turning into CO2 gas, and doesn't really matter, I'll just write liquid. So how do you want to balance this? What do you want to do first? What's that going to do for me? My carbons are now balanced. Now what do you want to do? Put a 4 in front of the water. What's that balance? The hydrogens are now balanced. And how many oxygens do I have on my right side? 10? We good with that?
5.
Right side, right side.
Oh,
10? And so what do I need to do to my left side?
Would,
Put a 5 there in front of the oxygen?
yes.
That'll give me 10 total oxygens. Okay, so if I start off with 25 grams of C3H8, 1 mole C3H8, gram C3H8. 12.011 times 3 plus 1.00795 times 8. 44.0966. So I'm going to write 1 mole propane. What am I going to put in the numerator here? Water. I'm looking for water, right? So I want to know how much water I'm going to create. Now what do I put in for the coefficients in front of those mole numbers? 1 for the propane and 4 for the water. Where'd that come from? These things, this section of the notes is called stoichiometric math or stoichiometric calculations. And that word stoichiometry meant what? It was German for balancing. So this is all, none of this works if I don't balance the equation. Sometimes you get lucky and the equation doesn't need to be balanced. There's just one of each thing. But if it's not balanced, you're not going to get the right answer. So I don't care about the number of moles. I want to know how many water molecules I actually have. So 15.9994 plus 1.00795 times 2. So 18.0153 grams of water times 4 times 25 divided by that 44 number. I get 40.9, so 41 grams of water. Okay. What would happen if I forgot to balance my chemical equation? This 4 number wouldn't have been here, right? I would have just wrote a 1 there, and then this would have been 10 instead of 40. So don't forget the balance. What? Okay. 180 grams mashed potatoes just doesn't really seem like very much. So let's say 600 grams, and we want to calculate the number of grams of oxygen needed to react with all that. All right, so what's the reaction for respiration? So C6H12O6 plus O2 CO2 H2O. This is actually actually, if we really want to do this correctly, since we're talking about eating, why is it aqueous and liquid? Well, where's this reaction happening? In your cells. So there's a bunch of water there. So the glucose is dissolved in the bloodstream and in the cytoplasm in this case. The oxygen must be dissolved in the bloodstream and the CO2 must be dissolved in the bloodstream. What if those things aren't dissolved in the bloodstream? What if they're in the gaseous phase? Would that be a bad thing? That would be a bad thing. We'll talk about the bends next set of notes, but if you had an air bubble in an artery or a vein or God forbid, a capillary, bad stuff can happen. Bad stuff. Okay, so what do I need to do to balance it? Okay, let's put a 6 in front of the CO2, and that balances out our carbons. Then what? 6 in front of the water to balance out our hydrogens. And so what's that give us for oxygens? 18. 18 on the right, and I've got 6 of them in the glucose molecule on my left, so then I just need a 6 in front of the oxygen, and it gets balanced. Okay, so I'm going to take 600 grams of glucose, and then for every 1 mole of glucose, what did we figure out that was? 180.158 grams of glucose. And then for every 1 mole of glucose, I've got 6 moles of oxygen. And then for every 1 mole of oxygen, it's grams of O2, 15.9994 times 2, 31.9988 grams O2 times 6 times 600 divided by 180. 639 grams of oxygen. Are we good with that? Yeah.
6 moles of oxygen. You said that you have to look back at the equation after you balance it, right? To get you have to balance the equation before you do it.
Correct. I needed to balance the equation so that I knew that the number that goes right here is that number right there. And this number that's right here is that number right there. So I can't get this part of the equation, this railroad track, correct unless I've balanced the equation. Does that seem like a lot of glucose? A lot of oxygen? There's a lot of warm human beings around Thanksgiving, right? Why? This reaction is exothermic, right? Are we okay with that, me saying that? This reaction gives off energy. So if you're consuming a boatload of energy and not doing anything with it, how does your body not kill itself by going to 105 degrees Fahrenheit? You just like, it's radiating. Like stand next to a person after they've eaten Thanksgiving, you can feel the heat coming off of their body. It has to. Going outside after you've eaten a huge meal feels good when it's cold. Why do you not really want to eat when it's hot? You can't dissipate the heat. That whole, I don't want to swim after I just ate is just stupid. Because you do want to swim after you just ate, because that's a really good way of pulling the heat out of your body. Okay.